back. This is Unit 5.3, and this is Ideal Gas Laws. And pages in a book you need to read are 474 to 499, and the workbook pages are 199 to 213. And before we get started, I just want to apologize. I am getting hoarse. I'm losing my voice, so if I have to clear my throat a little or my voice disappears, just bear with that. All right, so getting started. So this section is talking about an ideal gas, and this is the ideal gas law. And this is a gas that behaves perfectly according to the postulates of the kinetic molecular theory that we talked about in 5.1. So what is the difference between an ideal gas and just a regular gas that we talked about in 5.2? Well, all gases are going to act in an ideal fashion unless it gets really, really close to the phase change temperature, which would either be a very low temperature or a very high pressure. Okay, so an example of that is that the cooling of water vapor near or below 100 degrees Celsius will cause it to become a liquid. So when you have a gas, water gas, that is very near 100 degrees Celsius, it will start to condense, and that's when it may not behave perfectly according to the gas laws. So that's what an ideal gas is. So all gases act like ideal gases until they approach a phase change. All right, so the ideal gas law is PV is equal to nRT. So if you'll pause this and write down that equation and then what each one of those variables stand for. All right, so the short, you'll hear this referred to as PIV-NERT. PV, PIV, and nRT, NERT, PIV-NERT, the PIV-NERT equation. So P is pressure, and pressure can be in one of 3 units. Okay, so now we're not talking about PSI or torr. Okay, so the units for this have to be in either millimeters of mercury, mmHg, kPa, or atmospheres. And I'll show you why in just a moment. All right, volume. V is volume, and that's still in liters. N represents the number of moles. Okay, N is if you'll remember back to when we were talking about moles, N is the abbreviation for moles because we can't use a lowercase m because the lowercase m is meters. Okay, so they just defaulted to the next letter, which is N. All right, R, capital R is the ideal gas constant, which I'm going to talk about in just a moment. That's why it's asterisk. And then T, of course, is temperature, and that must be in Kelvin. All right, so I put an asterisk here that the pressure units for the ideal gas constant must match the units that are in the problem. So what do I mean by that? Well, here's the ideal gas constant. Now there's 3 values for that. This value, and this value. And this is in your reference materials in that constants and conversions column that I showed you earlier. That has all of the 760 torr is equal to 760 mmHg, which is equal to the other kPa, etc., atmospheres. So the only difference between these is the unit for pressure. And I'm circling them right here. Okay, so in our problem, let's say that the pressure is given in atmospheres. For these ideal gas law problems, if the pressure is given in atmospheres, then it's this value for the ideal gas constant that we're going to use. So that'd be 0.0821. If your units for pressure is given in kPa, which is this middle one right here, you're going to use 8.31. And if the units are given in mmHg, you're going to use 62.4. So you just have to look at the units to know which ideal gas constant to use. If it's not given to you in one of these 3, let's say it's given to you in PSI, well, there's not an ideal gas constant for PSI, so you're going to have to convert PSI over to one of these 3. And it doesn't matter which one you convert it over to. Just convert it over to one of those 3. All right. So let's look at some problems. Now, unlike 5.2, 5.3, there's not a change happening. So what they'll do is they'll give you, like, say that there is a gas that is at this pressure and at this volume, and at this temperature, how many moles of that gas do we have? So there's not a before and an after. It's just, here's the situation. Here's one missing variable. What is it? All right. So we're still going to use glues to help us determine how to get the answer to this, step by step, dissecting the problem to help you solve these. All right. So what is the pressure in atmospheres of a sample of 0.20 moles of oxygen gas that occupies a volume of 4.1 liters at 40 degrees Celsius? So, glues, first thing we're going to do is circle our givens. All right, so there's our givens, and we're going to list them out. So 0.20 moles, okay, and that's going to be equal to the value N, the variable N. 4.1 liters, that's going to be a volume, and 40 degrees Celsius, that's going to be equal to your temperature. All right, so now, what is our unknown? What is the pressure in atmospheres? So our unknown is pressure in atmospheres. Now this atmospheres is important because the ideal gas constant, R, we're going to have to look that up and use the one that's atmospheres. Okay, so if we go back and look at that, that's going to be this one, atmospheres. So we have 0.0821 liters atmospheres over moles Kelvin. And these are the units for the ideal gas constant. It's very important that you write all the units down. Okay, so 0.0821, and I'm going to erase the R there. Liters atmospheres over moles Kelvin. And I'll show you why that's important on those units, and that's equal to R. All right, so we have those listed out. We have our unknown identified. So the next thing we do is our equation. Well, this is the Pivnert equation, PV equals nRT. So what are we solving for? We're solving for pressure. So I'm going to put a box around that because I don't want to move it. I'm going to lock it in place. So I need to get rid of my V. So if I divide both sides by V, V cancels, and we have pressure is equal to nRT over V. All right, so let's check our units, make sure they're correct units. Moles, okay, check. Volume is in liters, check. Temperature is in Celsius. Okay, we can't have that. It has to be in Kelvin because look at the units for the ideal gas constant. Right there is K, so that reminds you that the ideal gas constant has to match the units that are in the problem. So in order to change 40 degrees Celsius into Kelvin, we have to add 273 to that. So we're going to get 313 Kelvin. Okay. All right. So now we can plug everything into this equation. So moles, we're going to have 0.20 moles times the ideal gas constant, 0.0821 liters atmospheres over moles Kelvin, and I run out of room, times, I'm going to put it over here, temperature, which is 313 K, over the volume, which is 4.1 liters. Okay, so now we need to cancel what we can cancel. So moles is going to cancel with moles here. Liters is going to cancel with liters here. Kelvin is going to cancel with kelvins here. And that's going to leave you atmospheres as your answer. And that's what the question is asking for. Now, if you mistakenly used a different ideal gas constant, like say you use the one for kPa right here, you used 8.31, then you're going to get your answer in kPa. Then you would have to convert that over 2 atmospheres. Okay, you would have to use the conversion of 14.7 kPa is equal to 1 atmosphere. So just make it easy on yourself. Use the correct ideal gas constant so it gives you the unit you want for your answer. Then you don't have to do another conversion. All right, so let's do the math on this. So grab your calculators. We have 313 times 0.20 times 0.0821 divided by 4.1. Okay. It's going to give us 1.253526829, which is just the raw answer. It's not the official answer. We have to count sig figs. So here we have 2. Here we've got 2. Here we have 1 sig fig. 40 degrees Celsius is 1 sig fig. So our answer is going to be in 1 sig fig. So there's 1 sig fig right there. So this 2 tells us whether we round that or not, and it does not. So our official answer is 1 atmosphere. Okay. Next question. I'm going to circle my givens. I'm not even going to read the problem yet. Okay, list these out. 2.0 liters is equal to my volume. 20 degrees Celsius is equal to my temperature. 720 millimeters of mercury is equal to my pressure. All right, and then what's our unknown? What is the mass of the sample? Okay, so I want mass, question mark. All right, mass is related to moles. So if we think about this, this is our mole map, remember? This is mass, and this is moles. So you're going to have to think ahead on this. This is particles, and this is volume, which doesn't matter on the mole map for now on this problem. So it's asking us to solve mass. Well, we can get to mass if we solve for moles. We know moles is part of PivNerd. It's the N in PivNerd. So we're really going to be solving for N. Then we're going to have to do another conversion to solve for the mass. So in this problem, it's going to have, we haven't read the problem yet, but in this problem, it's going to have to tell us what the gas is in order for us to convert that over. So if you'll look at the problem, the gas that it's talking about here is hydrogen gas. All right. So we're solving for mass. So the next step in PivNerd is the equation. So this is PV equals nRT. Okay, we're solving for moles. So we're going to divide both sides by RT. It cancels RT out there. So checking our units, mmHg for pressure is good. Temperature, 273 plus 20 is 293 Kelvin. So that takes care of our temperature. All right, so for our R, we need to use the mmHg. So let's look at that. The mmHg is 62.4. So 62.4 liters mmHg over moles Kelvin. All right. And so pressure, let's start plugging stuff in. 720 mmHg times volume, 2.0 liters, over 62.4 liters mmHg, oops, I almost wrote atmospheres, over moles Kelvin, times the temperature, 293 Kelvin. All right, so let's cancel what we can cancel. So mmHg cancels mmHg, liters cancels liters, Kelvin cancels Kelvin, so moles is what's left. Okay, so when I get my answer, it's going to be in moles. I'm going to put it over here because I know I'm going to have to do another conversion. Okay, so grab your calculators. $720 times 2.0 divided by 62.4 times 293. So this is going to be, I'm going to put it right here, 0.0787608.296 moles. All right, I'm going to rewrite it over here, 0.078608296. We're not going to round this yet, moles, because we need to convert it to mass, which is grams. All right, so I already showed you the mole map. We know we can go from moles to grams. All right, so 1 mole of hydrogen gas is how many grams? Well, hydrogen gas is a diatomic element, so it's H2. You have to remember the diatomic elements on these gases because most gases are diatomic elements. Most, not all. So H2, so we have 2 atoms of hydrogen. Each atom is 1.01, so that makes the mass 2.02. All right, moles cancels here, so we take our answer and multiply it by 2.02. That's going to give us 0.159096, etc. We don't need that many numbers because we're rounding. Now this is our final answer, so we round it to sig figs. So 2 liters is 2 sig figs. 20 degrees is 1 sig fig. You can't get any lower than 1. Okay, so there's my 1. This 5 here tells us if we round that 1, and a 5 does round to 1, so it's 0.2 grams is our final answer. Okay. Now on these videos, you can go back and re-watch these examples that have been worked out for you if you're trying to work out one at home instead of in class. So you can go back and look at this again. All right, and so sometimes they ask you the density of the previous gas. All right, so remember density is equal to mass over volume. So our mass of our gas, we get from this answer, it's 0.2 grams divided by the volume. Our volume is 2 liters, 2.0 liters. So if we just do this, 0.2 divided by 2.0, we're going to get the density of 0.1 grams per liter. Grams per liter. There's your unit for that. All right, and one last problem. We have 5 liters here, 3 atmospheres, 100 degrees Celsius. All right, so here it tells us that it's O2, that's oxygen, and it gives us the molar mass. So that's going to be important. Okay, so I'm going to go ahead and circle that. Even though we're not going to use it in our initial calculation, we will use it because what is the mass? So we have to use the molar mass again. All right, so let's list these out. 5.0 liters is equal to a volume. 3.0 atmospheres is equal to our pressure. 100 degrees Celsius is equal to our temperature. We know that's got to be in Kelvin, so I'm just going to 373. I'm going to immediately, and you can do this as well, you can just immediately start converting these over if you know they need to be converted. At this point, you should be able to recognize that. All right, and so what is the mass? So on this previous problem, we saw that mass is related to moles. So the question mark we're solving for initially is going to be moles. All right, so we're going to need our R, and this is in atmospheres. Okay, so we're going to go back to the ideal gas constant. We're going to use the ideal gas constant for atmospheres. Okay, so it's 0.0821 liters atmospheres over moles Kelvin. It's going to be my R. All right, so our equation PV equals nRT. We're solving for N, so we're going to divide both sides by RT to get rid of it. So pressure, 3.0 atmospheres, times volume, 5.0 liters, over 0.0821 liters atmospheres over moles Kelvin, times the temperature, 373 Kelvin. All right, cancel what you can cancel. Atmospheres cancels atmospheres. Liters cancels liters. Kelvin cancels Kelvin. Our answer is going to be in moles. I'm going to put it right here because I know I need to convert it. All right, so we pick up our calculators once again. 3.0 times 5.0 divided by 0.0821 times 373. Okay, so I'm going to get 0.4898231085. Okay, I want to get rid of moles, so I'm going to put on the bottom, converting it to grams. 1 mole is, here's where this information comes in, 32 grams. All right, and so we're just going to multiply this by 32. We're going to get, I'm going to put the answer up here, 15.6743. That's as many numbers as we need because we have 2 sig figs for the volume, 2 sig figs for the pressure, 1 sig fig for the temperature, 100. That's 1 significant digit. So our answer is only going to be in 1 significant digit. So 15.6, that first one right there is the 1 significant digit. So we look at the 5 to see if it rounds. It does round that. So it's 2. This becomes a 2. We can't just drop that 5 off because it's before the decimal. So as I said many times before, we had to have that as a placeholder 0. So the answer is going to be 20. And we converted it to grams. Grams. It's going to be our answer, our final answer on that. All right, so that is 5.3. We're dealing with ideal gases. And make sure that you, I know that a lot of students are trying to watch these videos on Canvas, and Canvas does, I embed the video. For some reason, Canvas doesn't show the video if you're watching it on your phone. So the best way to watch this, if you're going to use your phone, is to make sure that you slap that like button right across the face. Make sure that you subscribe and hit that notification bell so that you know when I put these up on YouTube, you can watch these on YouTube instead of on Canvas. All right, see you next time.